Now we are going for the microstrip antenna. Okay. So in microstrip antenna, I'm going to bifurcate into three parts. One is the basic characteristics and feeding methods. And our focus will be on very first is the feeding methods. What are the feeding methods? So we'll understand what are the basic characteristics of the antenna. Okay. So basic characteristics of antenna, then feeding method. What are the feeding methods are there accordingly. Now we will go one by one. So initially we will understand that is what is microstrip antenna and what are the basic characteristics of microstrip antenna. So you can ask the question in between if you will have. It is very easy topic. So initially we'll understand what is microstrip antenna. Microstrip antenna are low profile. They are conformable to the planar and non-planar surface. Then it is inexpensive to manufacture using modern printed circuit technology, then compatible with MEMS that is MMIC design, and then it is variable or reconfigurable. So we'll understand, discuss this, what is this. So microstrip antenna are low profile, means they are the planar structure. They are the conformable. So what do you mean by the conformal antenna? Conformable. So the best example to explain this is what the aircraft. In the aircraft, if we will take an example of fighter plane, there are around 70 antennas, 70 plus minus. And in the domestic aircraft, there are more than 40 different antennas. Now the aircraft is what main thing is the aerodynamic property. If the aircraft is there, then the shape of antenna, mainly it is on the surface of the aircraft. And if you are using horn antenna, helical antenna, or any such dish antenna, so it will be very difficult for the aircraft to protect the aerodynamic property. So what to do? So for that, mostly the microstrip antenna or the planar antennas are used. Now this microstrip antenna, if this is the structure of, if this is the surface of the aeroplane, so on the surface it is kept with the same shape. So this is called the conformal, that is conformability. Based on the shape requirement, it kept accordingly. Or in microstrip antenna, it is used in your cellular phone. So whatever the size and all these constraints, so that is a simple strip. Okay, so this is what the basic advantage of the microstrip antenna is, what it is conformable. Then inexpensive to manufacture. So now printed circuit board technology, PCB manufacturing. So it is same as the PCB manufacturing. If you will use the different material, then the epsilon property, that is the dielectric constant, can be varied. Then another important thing is it is compatible with the MEMS technology, that is microwave integrated circuit. MIC means microwave integrated circuit, and M stand for monolithic microwave integrated circuit. So this is monolithic microwave integrated circuit, MMIC, or previously it was HMIC, hybrid microwave integrated circuit. Now ICs, we can say that the integrated circuits are designed for the low frequency application, but for the high frequency application there is a specific technology, specific material of IC can be used for monolithic. So that technology is microwave integrated circuit. So this simple IC, that is VLSI and all these things, cannot be used for micro integrated circuit because the frequency is very high, so it requires a different treatment. Now, so this micro integrated circuit, it has a chip and it can be very easily integrated with the microwave circuit. For what? With the antenna. For what purpose? For the purpose of reconfigurable. that is variable, means reconfigurable, means that is a reconfiguration in frequency, impedance, polarization. Uh, for such, you can have use the pin diode or the vector diode. Means what? Suppose if you want to use a antenna for two different frequencies, but not at a time. So you can have a diode, that is pin diode or the vector diode. So according to adjustment of, you can use for, that is called frequency reconfiguration. So this antenna can be used for this band initially, then by doing tuning electronically by the vector diode or the pin diode, it can be shipped to the another range of frequency. So you can have the two range of frequency can be operated on the same antenna with whatever the size are there. By tuning the vector diode, you know that the capacitance can be varied. So accordingly, the antenna properties can be varied. So this is what the shifting of the frequency or impedance also, and other parameter polarizations also. Sometimes we require different polarization technique, that is circular polarization or linear polarization. So accordingly, these diodes you can use, or it can be integrated with MMICs. So this is what the major advantage. These are, you can consider the advantages of the microstrip antenna. But there are certain disadvantages also. So what are these? Okay, so the question is detail how same antenna can be used for the different frequency band. Okay, so same antenna, how the same antenna can be used for the different frequency band. So I'll just explain it. Suppose this is what one of the antenna, okay, and this antenna is using for one frequency band. So this is what x and y axis, and you will use the antenna for this frequency band. This is what your frequency, and this you require another frequency band. Okay, this is what your threshold. You can see. So this is what your threshold. Now my requirement is, this is my center frequency. That is, I can say this is F1. This is my frequency band. I'll say this complete band is F1 and this band is F2. Okay. Now whatever the antenna you are using, this is simply the microstrip antenna having the same approach. Initially, if you are tuned for this frequency, okay. So if it is working initially for this particular frequency, now I have to tune it for the another frequency. Okay. So for the, I'll give the example. Example is this your phone, okay, or a general example you can say. That is, suppose you are using a Wi-Fi as well as cellular application, and if you want to tune it, or any frequency band, you can take any frequency band. Generally, these are the closer to 0. So if you are using at this frequency range, and if you will add the capacitance or adjust accordingly, then it will tune to this frequency. So you can use for this frequency band, the physical dimension of the antenna will remain same, but you can change it to the another this. Okay. So any external property of the antenna can be changed. So this is what I am saying in terms of the frequency. Or sometimes you can have some linear polarization or the circular polarization. That way also you can change. How the tuning is happened, this is what the question. So this tuning happened automatically. Automatically means it can be switch, can be programmed according to the requirement, or can be done manually. Okay, if you want to tune it what you can say, simultaneously. So accordingly, this tuning can be done. Okay, so it can be programmed. So program means you can set the capacitor having the gate and the driver circuit such that it will give the voltage to the capacitor, and capacitance levels will change, and accordingly antenna will tune for the different circuit. So that is based on different application it can be done. Okay, I hope I have satisfied your query. Is it? Okay. So thank you. So here, what are the disadvantage of the antenna? So the disadvantage of antenna is a low efficiency, low power, and high Q. Now, what is this low efficiency and low power? Now, you just assume this is a simply a planar structure like a paper. Okay, simple like this paper. The PCB board, you know the PCB board. So this PCB board cannot handle very high power because whatever these layers that are a few microns. So power handling is not possible. As if you will say the dish antenna, horn antenna, helical antenna, and the physical antenna having the different shape, they can handle a large power, but the microstrip antenna cannot handle the large power. Then the efficiency, so low power handling and efficiency. Now efficiency, as just now we discussed that the highest efficient antenna, you can say the horn antenna, it is maximum up to 80%, and it is lower than that, maybe 50-40% of the efficiency of this antenna is there. So this is what one of the drawback of the microstrip antenna. High Q. So quality factor, Q means quality factor. It is more than 100 sometimes. So if your quality factor is high, then bandwidth is low. So ultimately what you can say, it is acting for the narrow band. So again, this is the disadvantage. But by some combinations and by the modification, again, the researchers are working for the bandwidth enhancement, so can be resolved, but it has high Q. So for the basic antenna, this is what the disadvantage. Poor polarization purity. So if you are designing the antenna for polarization, so whatever the polarization suppose you are using it for the circular polarization, so cross field component is there. So in that the cross field component is there. So due to that, whatever the problem of polarization mismatch is always there. So this is what the problem here, that is the polarization mismatch. Our polarization is poor and poor scan performance. So sometimes the antenna can be used for the scanning. Scanning means navigation purpose. Okay, you can say the radar antenna, they are moving entirely taking 360 degree. So for scanning, it has the poor performance. So generally for scanning, this is not used. Then spurious field radiations are very narrow frequency band. Spurious field radiations are there, so it is narrow frequency band. Polarization. Okay, you want quickly the polarization. Okay, so what is polarization? I have explained previously, but anyway, as you require the polarization, give me a minute. I will quickly go for the polarization. For the polarization, simple, there are two types of polarization: linear polarization and what you can say, okay. Wait a minute. Is the screen visible? Full screen is there? Quickly, anybody can respond.
Yes, yes, visible.
Okay. So quickly, I'm going for the polarization. Now, this is what the linear polarization, linear horizontal polarization. So this is what here you can see the red line and the green line. So the red line is the electric field component, green line is magnetic field component. So you can say this is E, electric field intensity, and this is H, magnetic field strength, and they are perpendicular to each other and they are propagating vertically. So all the direction they are perpendicular to each other, electric field, magnetic field. Now the polarization is the property, graphical representation of how the electric component is varying. So this is what the linear polarization. So you just represent here the electric field. So electric field is here. So this way it is representing. So this is linear polarization. So this is linear horizontal polarization. Now the second is, this is vertical polarization. Again linear, but it is vertical. Suppose I am having this as the antenna. If my polarization, if it is polarized this way, so this is horizontal, this antenna. If I will keep this way, it will polarize this way. So this is the vertical. So simple by considering the antenna. So this type of polarization is the linear and what you can say in linear, vertical and horizontal. This is what the linear polarization, vertical and horizontal. And this is what the circular polarization. Now the electric field component is split into two parts and it is rotating this way, left-handed circular polarization. You can in detail, I'll just brief here. If you want, I have put up the lecture in the what you can say on the YouTube, so you can refer that, so you will get in detail. So this component, it is completely rotating. So as compared to this linear component, this is horizontal or vertical, this is the addition of these two. You can see this you can see if this component, this vertical component takes this horizontal, and this is what the resultant component. So by adding these two, it is what this circular polarization. If the direction, if the angle between these two is 90 degree, then it is what left-handed circular polarization. Okay, so yes, antenna is radiating in linear polarization, or antenna may radiate in the what you can say the circular polarization. So what this polarization exactly it should do in this way? So they are not purely there. So it may be the elliptical polarization. You have to struggle a lot in microstrip antenna for doing the polarization, getting the polarization. Am I clear now? So this is what the quickly I have explained the polarization. Now we'll come back to our microstrip antenna. So this is what poor polarization, purity. Purity is the thing. So if it is mainly, it is with the circular polarization. So if it is circular polarization, so it will may not be the complete whatever the circle is expected. So you are expecting this circle in this, so it may not be the exactly circle. It may be like this, maybe the elliptical. The component are not the same, it may be in the elliptical manner. So this is the task we can say in a poor polarization purity. But yes, definitely these problems are also, the various people are working on this and trying to get the polarization purity. But it is as compared to the other antenna. This is what the comparison. Then spurious field radiations are very narrow frequency band. So due to the spurious field radiation, what is spurious field radiation, that I'll explain later on. The frequency band is narrow for this antenna. So these are the some of the disadvantages. So as I explained, you can elaborate this. Don't put in the answer book simply the heading. You have to elaborate what I explained. So for that, repeatedly you can see these videos which I'll upload on the YouTube. Now basic characteristics. Now here basic characteristics of the antenna, that is the microstrip antenna, we'll discuss. Now what is the basic characteristics here that whatever the dimensions are there. This is what your patch antenna. Okay, so this microstrip antenna is also called the patch antenna because here this is what a patch-like structure. So that's why another name is patch antenna also. Now height. So this is the top view and this is what the side view of the antenna. So this h is the height. Okay, so this h is there. So this is what the height. Again, it is lambda dependent. So everything is lambda. So lambda 0 is the free space wavelength. So if your wave is radiating in the free space, so that is called the free space wavelength. If it is in free space wavelength. If it is going through a medium, maybe you can have the waveguides, that is the hollow pipe, and if they are going from that, so that is the waveguide, that is called the guided medium. Or if they are on the antenna, so that is also. So for the calculation, we are considering here the free space wavelength. So that's why it is lambda 0. Okay. So any antenna dimension is lambda dependent. So this is called the electrical dimension of the antenna. Electrical dimension means if you are changing the frequency of operation, your lambda will change. You know that your lambda and frequency is related by the c. C is speed of light. So anyone can give me the equation that is between lambda and c, lambda and f frequency. What is the equation which we have discussed? That is very basic equation. What is lambda equals to?
Frequency by speed of light.
Yes, c by f. No, c by f. C equals to not lambda. C the lambda equals to c by f. Okay, so that way you can see. Yes, correct. C by f. Lambda equals to c by f. Correct. So this is what the so as you will have the higher frequency, lambda is very narrow, inversely related by the c. C equals to 3 into 10 to the power 8 per meter second, meter per second. So if your height of this substrate, that is what the substrate means dielectric medium. So this dielectric property you can change the epsilon r. So that also I will put. So here height of this substrate is 0.03 lambda to 0.05 lambda. In this range you can select. So it has some design constraints. By increasing the height, what will happen? By decreasing the height, what will happen? So generally the height is standard. Some standards are available. These standards are around 0.65 mm height or 0.5 mm height. That thickness of the material generally available. So FR4 and all these things. So this is one is for the general constraint for the height. Another is the length. So this is what the length of antenna. Here the feed is given. Here you are giving the feeding, the input, and this is what called the length of the antenna, and this is width of the antenna. So this length of antenna is in this range, that is lambda by 3 to lambda by 2. So based on the various combinations and all these things, the designer, RF designer, they choose the lambda in this range. So again, it is frequency dependent. Epsilon value. So it is in 2.2 to 12. Okay. In this range, whatever the epsilon means, the material, different material has different property. Suppose you are taking Teflon, so it has epsilon property 2.2, 2.1. Various Teflons are there. If you will take the FR4, I think 4.1, 4.2 are the FR4 dielectric property. So based on which material you are taking as a substrate, your epsilon value is there. So initially you have to take the epsilon. Okay, so these are the some parameters. Okay, these are the some parameters and their range. So epsilon value is 2.2 to 12. So if you will take very high epsilon, then it may have what constraint. So in the design, we can designer think based on this parameter. Now, the shape of the microstrip antenna. There are the various shape of this microstrip antenna, not limited to only this shape. There are various other shapes of the microstrip antenna. These are the basic: square, rectangular, dipole, circular, elliptical, triangular. There is disc, the circular ring, and the ring sector. So these are some of the commonly what you can say the things. Uh, what is the question? An antenna having gain of 6.7 dB and front to back ratio is 11.7 dB and resonating at 2.4 gigahertz. This is the design constraints. So if your antenna, this is what the design requirement somebody has put. The question that is, I think Akash has put, an antenna is having gain of 6.7 dB and front to back ratio is 11.7 dB and resonating at 2.45 gigahertz is suitable for some specific application. Okay, so this is what antenna design problem. Gain is given, gain is taken at 6.7. So gain requirement is 6.7 and front to back ratio means this is what the lobe, whatever the lobe you are saying, that is radiation resistance, whatever the radiation pattern you are saying. So whatever the radiation resistance is there, so front to back ratio is 11.7. Generally, it is 14 is the standard, and the resonance frequency 2.45. So it is ISM band. So this is for the ISM band. So this is free band used for the various application. So front to back ratio means the whatever the side lobes, limitation of on the side lobe, whatever the side lobes are there, that side lobes can be limited up to by this. Okay, you want me to draw a diagram? Okay, give me a minute. I'll draw here. Now, this is 1 minute. Now, this is what you can say a radiation pattern. Okay, this is what the main lobe, this is the antenna, and this is what your back lobe. This may be your side lobe. This may be your side lobe. Now, if your side lobe is this is what one condition. If your side lobe is very prominent, this one, this is what another one. So it is comparable with almost your front lobe. This is what your front lobe, okay, is radiating in this direction. Now, what is the requirement? 11 point something dB is the requirement. Now, whatever your front lobe is at, it is taken as the electric field at here, and your back lobe is at here. So whatever the ratio of front to back, that should be in that the requirement. So generally, it is taken in the what you can say in electric field normalized manner, and from the normalized it can be converted to the dB. Okay, this has happened. So this is called the front to back ratio. Is it okay, Akash? Okay. Anything else? Any question? So this is front to back ratio. Okay. So this way it is taken. So these are the characteristics, basic characteristics of the antenna, and these basic characteristics are considered here. Now we will go further. These are the various shapes. Now what shapes we are going to discuss here? We are going to discuss here the square and the circular. So these are two examples, design problem we are going to consider, square and circular. If you want to take a project and various other shapes, you can try and you can go for the various other shape calculation. Okay, this is what the general constraint. Now, the feeding methods. Now this antenna here is feed here. Okay, this is the input given to the antenna. Now microstrip antenna, there are some different feeding methods. So these four different feeding methods are there for various application based on the requirement of the application. They can use these four different techniques. We'll discuss these four. Each one of these we can discuss, and microstrip line feed, probe feed, aperture coupled feed, and proximity feed. So generally microstrip line feed and the probe feed, these are the popular, and the aperture coupled and proximity, these are somewhat complicated. So they are generally rarely used. But these microstrip line feed and probe feed are popularly used. Okay, so what is that? Now I'm giving here the microstrip line feed. So microstrip line feed and its equivalent circuit here. Now microstrip line feed is this. Now what is this? The microstrip. This is what your antenna, whatever your patch antenna. Now feed is the input. Whatever the input you are giving to the antenna. Question is, what is feed? Feed means input. We are giving the input to the antenna, because if you are considering a transmitting antenna, we have to give some input, that is the radiating input to the antenna, and whatever that input we are giving, that is called the feed. Okay, and this is what the feed technique. So actually this is what your antenna, basically whatever your antenna is this much from here, whatever this square patch. So this square is your antenna, and this is what your the substrate. Okay, this is what your substrate, and this is what your ground plane. So exactly how this antenna is there. This is printed. Yes, this is a printed antenna. I'll explain you how this is. So simple. This is what substrate. You can say this, whatever this material you are seeing, this is what the substrate, the thickness. Now something is printed here. Okay, so you can have a printing of antenna here. Something, some shape, something. Okay, let's suppose this is the rectangle. Whatever the square, this is printed. Printed means the copper material is here, and the back side here, back side you can have again the copper. So back side here it is a copper. So it is simply like a two-sided, both-sided printed circuit board. Okay. So yes, it is two-sided printed circuit board. Printed transistor on substrate. I don't know, but it is two-sided, double-sided PCB. As you have the copper on this, copper on the upper side and copper on the back side. So the back sided, it is completely plain. Means the copper is there on the entire patch, and here on the small portion the copper is there, and thickness is there. Some thickness is there. So this way we can consider it. Okay, so this way it can be considered. Now this feeding, this patch is there, whatever the patch. So this patch is considered. So this patch is there. Now this patch is at the center. The substrate is, this black line is the complete ground plane, that is again the copper plate. Now this feeding line, this is the microstrip line. It is at the microstrip line. It has some length, whatever the length should be there, and whatever this patch, this what you can say khacha or something. This is what made whatever this particular design is made. It is for the impedance matching. Means whatever the impedance of this line should match with the impedance of patch. Just now we have discussed the input impedance, so the matching is required. So it has the calculation. So by the impedance matching calculations, you can find it out what should be the length, what should be this thickness, this width. So accordingly, this is specifically designed. Okay. Now, this is one of the technique. Its equivalent circuit is this. This is what the inductor, resistor, inductor, and capacitor. So by this, it has which direction it will radiate. I'll just, the direction of radiations are shown. So here, this is what the radiation. So it will radiate this way and this way also. I will have, I think, the another radiation. You can see the radiation. So this is what the radiation. So this is what positive, that is the upper patch, and this is what the ground plane. So it will radiate this way. It will go from upper and it will end. The electric, these are the electric field. Okay. So it will radiate from top and it will end at the bottom. This way, the radiations, and they are outside also. They are radiating this. So the radiations will be outside here, here. But electric field lines, they are starting from the upper patch, ending at the ground patch, and outside also. Okay. So this is what the way of radiation. So this way it will get radiated. Now, this is what the equivalent circuit for the transmission line. Now, this technique we can understand by the transmission line model. We will go further for the analysis of the transmission line model, what it is and how antenna can be considered here. So this is what the thing here. It is feed from here, and this is inductor, resistor, inductor, capacitor. So simply your transmission line model, you have studied the transmission line model. So this is what the equivalent circuit of microstrip line. So this is, that's why it is microstrip feed, and this is equivalent model of microstrip line. Okay, so this is what the feeding line. Then next feeding technique is the probe feed. Probe feed is what you can see here. This is what the patch. Now on this line you can see very correctly. So here the coaxial connector. So you can have the coaxial connector, N-pin connector, the other type of connectors are there. This is if you want to give directly a coaxial line, that is the cable which you are using to feed your CRO, to connect your CRO. So that is what the coaxial cable. So if you want to directly give a cable to the antenna, this connector, so this coaxial connector, so this coaxial connector is there. Now this is what the lower one is the ground part. This is what the negative part. Okay, so it is connected to the ground plane. Okay, as you have seen this, it is connected to the ground plane. And the center conductor in the coaxial line, the center conductor is connected to the patch here. Okay, this is what the patch. The patch is shown here, circular shape or maybe any shape, it depends on your design. So it is connected to the patch here. Okay, so this is epsilon r, the dielectric constant. The microstrip patch is this. So same is shown here on the top view. Dielectric substrate, this is what the dielectric substrate, this is connector, this is ground. So this way the connections are made, and this type of technique is called the probe feed, because here this is the probe is connected. So it is called probe feed, and it goes through. Okay, and this is what equivalent circuit, same as the previous. This is what the probe feed technique and equivalent circuit. Now the advantage of probe feed is it is easy to connect, but the mechanical strength and all this, if your antenna is very small, then probe feed may give you the mechanical strength problem. मतलब टेढ़ा हो सकता है, ऐसा हो सकता है. If your probe weight is more, then it may give you problem. So yes, what doubt you have, you can ask. Unmute yourself. If you have any doubt, you can ask. Akash? So you can directly ask, so it is easy for me. If you are related topic, doubt related to the topic. So this is what the coaxial connector, and the strength of the coaxial connector, the mechanical issue mainly that this is soldering is made here, so sometimes it becomes a dry solder or connectivity issue. So these are some issue with the coaxial connector, but the basic advantage, it is very easy to operate. Okay, so it is very easy to operate and you can have the use of it. So this is two technique, microstrip line and the pro feed. So these are very easy to understand. Then next is the aperture coupled field. Now this is what somewhat very specific. Now you have to imagine in a very focused way, then and then you can understand. Now here, these are the two substrates. This is epsilon R1 and epsilon R2. In some specific application, you can use the two substrate, and this is what your in between plane. So the microstrip line is in between, and here it is a slot. Okay, so the microstrip line has the capacitive coupling here, as the capacitor is shown here. So the microstrip line is having capacitive coupling. So by non-physical contact, it has the coupled. I'm repeating, it is non-physical contact. Means the between these two substrate, this dotted line is in between two substrate, it is kept. This is the microstrip line, and here the slot is made, and due to this slot, there is a coupling with this microstrip line, and this patch is get connected here, and this is what the equivalent circuit here. So the question is, if this antenna radiate from patch to ground, then why some EM wave does outside it, and if it is go, no, this is not the way. His question is, if it is radiating from patch to ground. So patch to ground, this is what the connecting. These are some of this intention of this diagram is something different. So that's why this diagram is given in this way. Actually, the radiations are forward. Okay, so suppose this is a patch. This is a patch antenna. This is a patch antenna. This is a patch here, and this is what the ground plane. So the thing is, it radiate from here and it go to the ground plane this way. So this way it is coming, but it goes in the front. It goes in the front. So its low mainly is the front lobe. But the radiation, I am saying the electric field of radiation is complete this way. This is only the direction of electric field. So it start from here, complete here. Start from here, complete here. But it goes in a front side. So it is radiating in the front side, but the diagram has some different intention. I'll explain you. So the radiations are this way in the front thing. Okay. So whatever the available thing I had, I have shared with you. Okay. So accordingly, the radiations are there. So this is what aperture coupled field. So this is aperture coupled field, and this is what the equivalent diagram. So you can say it is capacitive coupled. Now in in the that are not directly coupled. This is capacitive coupled. Okay, it is capacitive coupled. Yes, it is radiating a long way to receive some other antenna. Yes, it depends on the gain and the directivity property of the antenna. So this is the microstrip line, and this is what the aperture coupled field. Now the last thing what we are going to discuss, that is proximetry coupled field. Now this proximetry coupled field is what, again it is same as that. Again to what you can say, two substrate epsilon R1, epsilon R2, and in between you can have this microstrip line. Again the patch is there, only the ground plane is at the lower, and here the ground plane is in the between. So only that difference is there, and this is what the equivalent circuit. Again it is capacitive coupled. Okay, so this is what the proximetry coupled, it is called the proximetry coupled. Microstrip line is in between. This is what the substrate, upper substrate 1 having the value epsilon R1, lower substrate epsilon R2. So using two substrate is somewhat complicated. Means you have to calculate the effective epsilon R1. What is the property, what is the exact value by this and by this based on the height of this. So this is somewhat complicated to design, not that much easy as compared to the microstrip line feed and the probe feed. So in that you are using only the single substrate. Here two substrates are in. So this way it is simply given here. So this is what the proximately coupled field. So these are the four, you can say, technique, and these four techniques we are using. Is there any question? Directly you can answer. Okay.